Hi everyone. In this video we will talk about polarization of light. So I want to start with this first topic here, polarization theory. What do I mean by polarization? We'll then talk about the different methods by which light can be polarized. So first we'll go and talk about polarization by absorption, and after that we will do some problems over here as well. And finally we will talk about polarization by reflection, and Brewster's angle is something that we need to talk about. Okay, so these are essentially the ideas that we're going to talk about in this video. So let's start. So what is polarization of light? So if you remember, light is an electromagnetic wave, right? So light is electromagnetic wave, EM wave. And so what does that mean? Well, essentially light is a series of fluctuations of electric and magnetic fields. So for instance, if I go back to this picture over here, these purple lines, they show a fluctuating electric field. The electric field is fluctuating like a sine wave, and it's propagating. The direction of propagation is shown over here. So light has electric field that is propagating in a particular direction and fluctuating perpendicular to that direction of propagation, right? So light is a transverse wave, right? Transverse wave because the electric field or the magnetic field that forms light is fluctuating perpendicular to the direction of propagation. Right, so if I want to write an expression for the propagating electric field, I would write E vector, electric field vector, is some amplitude of the electric vector multiplied by a sine of kx minus omega t. Right, so this part is what makes this electric field a traveling wave. Right. So this is the traveling wave part of the electric field. And similarly, one can write a similar expression for the magnetic field. As you remember, the electric and magnetic fields for light, for any electromagnetic wave, is essentially perpendicular to each other. So we could pick either of them, either the electric field or the magnetic field, to talk about the light wave because we know that the other one is perpendicular to the first one. Okay, so now this is one single ray of light, which is shown in this picture over here. A second ray of light would also have electric and magnetic fields that are perpendicular to each other, but it's possible that a different ray of light has the electric field oriented in a slightly different manner. So for example, let's talk about a ray of light that is coming out of the plane of the paper. And I can represent that with a circle and then a dot in the middle of the circle. So the circle with the dot in the middle represents a ray of light that is coming out of the plane of the paper, so it's perpendicular to the plane of the paper, which means since electromagnetic waves are transverse waves, this ray of light can have the electric field perpendicular to the direction of propagation, so anywhere on the plane of the paper, which means that if I have an electric field vector that is fluctuating like that, then that can represent a transverse wave. So could an electric field that is fluctuating like that or like that. So there are many options for the direction of the electric field for a transverse wave that is coming out of the plane of the paper, right? So these are all representing electric fields for different rays of light. So we will call a beam of light linearly polarized if all the rays in that beam have electric fields pointing in the same direction. Right, so all rays have the E field pointing in same direction. Right, so that will be linearly polarized light. So one example of that would be if I have this as my direction of propagation of light, and let's say all the electric fields are always fluctuating like that. So different rays have electric fields that are fluctuating, but every time we measure the electric field, we will always find that electric field to be in the same direction. So that would be an example of linearly polarized light. Okay, but light can also be unpolarized. So unpolarized beam of light. So unpolarized beam would mean electric field is pointing in all possible directions. okay, in all possible directions. So what are the possible directions? Well, if light is propagating in a particular direction, then the possible directions for the electric field is always perpendicular to the direction that light is moving in. So if light is moving, for instance, out of the paper, then all possible directions mean any direction on this on the plane of the paper. So essentially, these are allowed directions for electric field, right? So for an unpolarized light, this electric field is pointing in all directions possible, right? Okay, so generally the light we encounter in our day-to-day life, for instance, sunlight, right? Sunlight or light from a light bulb, right? So these regular sources of light produce light that is unpolarized, which means that in that beams of light coming from, let's say, the sun, right? If we analyze a beam, we'll find rays with electric field pointing in all possible directions, right? Okay, so that's an unpolarized beam of light. All right, so that's about how light, the characteristic of polarized light. But now, is it possible to polarize light starting from an unpolarized beam of light? So in this example, we'll consider just that. So here I have a beam of light that is coming in over here. It's coming in, and it has electric field that can point in any possible direction that is shown in this figure. So that is an unpolarized beam of light, and it has some intensity I naught. So now we're going to make this beam of light that is unpolarized pass through a material that we'll call a polarizer or polarizing material. So what this polarizer will do is it will only allow the component of electric field in the original beam of light that is parallel to an axis called the pass axis of the polarizer. Okay? So if your electric field has a component that is parallel to the pass axis of the polarizer, then that ray of light will pass through. And so in the final beam of light that came out through the polarizer, all of the rays will have electric field pointing in the same direction, and so this would be polarized light. And how this happens is essentially the polarizer absorbs any ray of light that has electric field not along the pass axis of the polarizer. Okay, so that's how the polarizer polarizes light, by taking an unpolarized light and giving out polarized light. Okay, so this is an example of polarization by absorption, because essentially the polarizer material is absorbing light that is not parallel to its pass axis. So that's how it's polarizing the outgoing light. But this also means that the intensity of light will go down because the polarizer is absorbing a part of the light. Okay, so let's talk about putting in a second polarizer over here. So in the same path of that beam of light, I'm putting a second polarizer, but this time I've arranged the second polarizer to have its pass axis rotated relative to the pass axis of the first polarizer. Okay, so then the question is, what would happen when this polarized beam of light passes through the second polarizer? Okay, so it turns out that it'll stay polarized, but it will only, the second polarizer will again only let through rays of light that have components of electric field that is parallel to the pass axis of the second polarizer. Okay, but any electric field that I can draw can be resolved into components parallel and perpendicular to some arbitrary axes, right? So consider this electric field E1. So this is the electric field over here in the middle. And then let's say that this is the pass axis of the second polarizer, right? Pass axis of polarizer 2. Okay, so that's the pass axis. The angle between the pass axis of the first polarizer and the second polarizer is 60 degrees. We'll call it theta, an angle theta. Then the component of the electric field, E1, along the pass axis of the second polarizer is just equal to E1 vector cosine theta. And so the second polarizer will only let through this component of the electric field, which means that after the second polarizer, the rays of light would have electric field E2 is equal to E1 cosine theta, right? So this is E2, this is E1 over here, and this is how they're related to each other. Okay, so now what does this mean for the intensities? Remember, the intensity of light, I, is proportional to the absolute value square of the electric field. So I1 is proportional to E1 squared. Similarly, I2 is proportional to E2 squared. Okay, so this means that I2 is equal to I1 multiplied by cosine squared theta. And it's a squared because if you look at the relationship between E2 and E1, E1 is smaller than E2 by a factor cosine theta. But I1 and I2, they're related to E1 and E2 by a square. So if I go from this equation to comparing the intensities, then I'd have to write that I2 is smaller than I1 by a factor of cosine square theta. Okay, so often this relationship is referred to as Malus's law. So let's give a formal statement of Malus law. So what Malus law says is that intensity of polarized light goes down by a factor of cosine squared theta when passing through a polarizer, where theta is the angle between the polarization direction of the incident light and the pass axis of the polarizer. So that's the idea of polarization of light. We will now use this idea in problems on polarization. So in this problem, we will find a relationship between the three intensities I0, I1, and I2. So the first step, I think I'll choose the easier one. So the relationship between I2 and I1, that's kind of easy because we can just simply apply Malus law and write I2 equals I1 cosine squared of 60 degrees. Right, and cosine 60 degrees, if you remember, cosine 60 degrees is just equal to 1/2. So if I plug that in, then I get I1 times 1/2 squared, right? So this means that I2 is equal to I1 divided by 4, right? So that's the idea. That's the relationship between I2 and I1. Now let's approach the relationship between I1 and I0, right? That's a little more complicated because for I naught, there are all sorts of different polarizations that are available that it's coming in. But I1, there's only one polarization that stays, right? So now let's arbitrarily choose one of these arrows for I naught. So for I naught, I have a beam that is, let's say, coming out of the plane of the paper, and it has all of these different, and I'm only drawing a few because there's essentially infinite number of directions and I can't draw all of them. So let's consider this as a representative picture for my unpolarized beam of light that is coming in from the left side of the first polarizer, right? So let's pick a random ray, and let's say that its electric field is like that, and that electric field is, let's say, at an angle theta relative to the pass axis. So that's the pass axis of the first polarizer. So pass axis of polarizer 1. Okay, so if you take that angle and we apply Malus's law, then it says that the electric field that goes through, okay, so this is the electric field um, E0, right? So this is part of E0, so only part of E0, right? Part of, because there are all sorts of different rays that are coming in, and we picked only one such ray. So in that scenario, then we will find the particular electric intensity relationship is I1 is equal to I naught cosine square theta. Okay, but then we'll find another ray of light for which, let's say that this is some random angle theta 1. I'll find another ray of light for which this would be cosine square some other angle theta 2, right? So then what we should really do is we should average over all these theta values, theta 1, theta 2, whatever values theta can take. Okay, so now if I look at this picture, what values can theta take? Well, theta can either take values from I would have covered everything if I started from negative 90 degrees to 90 degrees, or 0 to 180 degrees, or even just if I took 0 to 90 degrees and then multiplied it by 2, right? So all of these will give you the same result. And so if I did an average, then that would tell me that I1 is equal to I0 times average of cosine squared theta. And that's how I'm going to represent the average. So this symbol over here represents average over theta. Okay. So how do I find this average? Well, what I have to do is, in order to average over theta values, I first have to add all the cosine squared theta values that are possible and divide by the total of all the theta values that are possible. And so a way of doing that is to write I1 is equal to I0 times integral over cosine squared theta d theta. And that theta then goes from 0 to pi divided by integral 0 to pi d theta. Okay. If you do this integral, you'll see that the result for this integral is 1/2. Now you can do this integral for any multiple of pi over 2. Just remember that the upper limit for both the integrals, both the upper and lower limits for both the integrals in the numerator and the denominator have to be exactly the same, and they have to be at least pi over 2 different. The upper and the lower limits have to be different by pi over 2. And if you do that, you will see that the ratio of these integrals is always 1/2 times, of course, there's the I0. So I1 is equal to I0 over 2. And this is always true in case of unpolarized light going through a polarizer. So unpolarized light through polarizer, so that gives final intensity is half the initial intensity. Okay, intensity. So now we can combine the results that we got so far in this problem. So the two results that we found is that I1 is equal to I0 over 2, and we also found that I2 was equal to I1 over 4. So if we combine these two results, then that gives me I2 is equal to I1 over 4 is equal to I0 over 8. So that is the relationship between the intensities of the three sort of parts of this beam, right? The unpolarized intensity, when it passes through the first polarizer, the intensity becomes 1/2 the unpolarized intensity. And then when the second beam of light passes through the second polarizer, the outcoming beam of light has intensity I2 is equal to I0 over 8. So the intensity goes down by another additional factor of 1/4. So in this problem, we start with an unpolarized beam of light and make it pass through two polarizers for which the pass axes are oriented perpendicular to each other, and we are expected to find the final beam's intensity. Okay, so in order to approach this problem, I'll first draw the polarizer. So let's say that the first polarizer has a pass axis oriented that way, right? So pass axis of 1. The second polarizer has a pass axis perpendicular to the first one, but I'm going to just do this for a more general case and say that the pass axis of the second polarizer is at an angle theta relative to the first polarizer. So pass axis of 2 in that picture, right? We know in this particular problem, theta equals 90 degrees in this problem, right? Because the two pass axes in the problem, the two pass axes are perpendicular to each other, right? Okay, so now the problem says that there is unpolarized light coming through the first polarizer, right? So this is the unpolarized light. We know that after it passes through the first polarizer, only the electric field that is parallel to the pass axis of 1 would stay, and then after it passes through the second polarizer, only the electric fields that are parallel to the pass axis of 2 will stay, right? So we'll have polarized light over here and polarized light over here. So how are the intensities related? That's the question. So if I have intensity I naught initially over there, then the intensity that remains after passing through the first polarizer, we know that that has to be I naught over 2, because a polarizer reduces the intensity of unpolarized light by a factor of 2 and makes it polarized, right? Okay, so now what happens if this I naught over 2 intensity light goes through the second polarizer? Well, we should get an intensity that looks like I naught over 2 times cosine square theta, right? And that is simply by Malus's law, right? So we just apply Malus law over here. Okay, but in this particular case, theta equals 90 degrees. So if I plug in theta equals 90 degrees, remember cosine of 90 degrees is equal to 0, right? So then if I call this one I1 and this one I2, we know that I2 must be equal to I naught over 2 times cosine square 90 degrees, which is equal to 0. Okay, let's do another similar problem. So this time we have 4 polarizers. The pass axes of these polarizers are at a relative angle theta, and we are supposed to find the intensity of the final beam after an unpolarized beam of light with initial intensity I0 passes through these 4 polarizers. Okay, so reading this problem a little bit carefully, it says that the pass axis is at an angle theta relative to the previous polarizer. So let's draw the 4 polarizer pass axes first. So this is, let's say, polarizer 1. Okay, so this is polarizer 1. And then I have the next polarizer, and it is at an angle theta, right? And I don't know what theta is, so our answer will probably depend on that theta. So this is theta, and this is polarizer 2. Okay, all right. So now we have another such polarizer. So this is number 3, and number 3 is relative to number 2. It is at an angle theta. So this was what was number 2, and so relative to 2, 3 is at an angle theta. Okay, so this is polarizer 3, and sort of in the same vein, this was number 3, and so number 4 is at another angle theta. Okay, and we are expected to then find um, sort of the intensity at the end. So we start with an intensity I naught over here. We know that as the initial beam is unpolarized, right? When that beam passes through the first polarizer, we are going to get a polarized beam with intensity I naught over 2. So that is known, that we understand. The second, going from the, after the first polarizer to the after the second polarizer, we're just going to apply Malus's law. So now the electric field is going to be along the pass axis of the second polarizer, and we'll get an intensity of I naught over 2 times cosine squared theta. All right. Now, when this second one passes through the third polarizer, we'll get intensity that looks like I naught over 2 cosine squared theta. That's the initial intensity before polarizer 3, and this has to be multiplied by another factor of cosine squared theta to get to the intensity over here. Let's give these names. So this is I1, this is I2, this is I3, and then finally we'll get I4. And going through I4, we see that another factor of cosine squared theta will apply. So we already had this after the third polarizer. So now this entire quantity is going to get multiplied by another factor of cosine squared theta. Okay, so we can now formally write down the relationships. I1 is I naught over 2, right? I2 is equal to I1 cosine square theta. I3 is equal to I2 multiplied by cosine square theta. These are all just applications of Malus law. So I4 is I3 times cosine square theta. So if I put all of this together, then I get I4 is equal to I3 cosine square theta, which is equal to I2 cosine to the 4th power theta, which is equal to I1 times cosine to the power 6 theta, which is equal to I naught over 2 times cosine to the power 6 theta. And so that is our relationship between the different intensities. When an unpolarized beam of light passes through two polarizers or three polarizers or four polarizers in this particular case. Okay, so a particularly interesting example is if the sum of all these angles is equal to 90 degrees, right? So in this particular case, what happens if the first polarizer and the last polarizer were at 90-degree angle, right? So this is 1, this is 4, and it is at an angle 90 degrees, right? But we have to divvy this 90 degrees up into three angles, um, right? So for instance, the first one was rotated by an angle 30 degrees. Second one was rotated by another angle. So this is number 2. So then 3 is rotated by another angle. This time, relative to the first, this angle is 60 degrees. Relative to the second one, it is 30 degrees. And so once we go through to the fourth one, we get 90 degrees. So in this case, what is the final intensity? Initial intensity is I naught again, and we have an unpolarized beam of light coming in. So in that case, of course, this result is going to be, as we said before, I4 is I naught over 2 times cosine to the power 6 of theta, but theta is 30 degrees in this case, right? It's just 30 for the first one, another 30 for the second one, and then another third 30 for this third one. So our result is simply an application of the problem that we just did before. And so we should get I4 equals I naught over 2 times cosine 30 degrees raised to the power 6. But cosine of 30 degrees, that is equal to square root over 3 divided by 2. Okay? So then I4 should be equal to I naught over 2 times square root 3 over 2 raised to the power 6. Okay, so if we simplify this a little bit further, we get square root of 3 raised to the power 6. That is the same as raising 3 to the power 3, which is 27. So we have 27 I naught divided by 2 to the power of 7. Okay, what is 2 to the power of 7? That is 128. So it is 27 I naught divided by 128. So that is our answer. We can simplify this by using a calculator. You can calculate what 27 over 128 is, but essentially this is the idea for finding out intensities with set of multiple polarizers. Okay, so the next topic would be polarization by reflection. And here, so what happens is it turns out that there is another way of getting polarized rays of light, and that is by polarization by reflection. So it turns out that if you have an unpolarized beam of light incident on a surface of interface between two materials, so in this case, let's say this is air and inside this is glass, right? So these are two different materials. As long as the incident unpolarized light is incident at such an angle that the reflected and refracted rays of light are at an angle of 90 degrees relative to each other, that's when the reflected ray of light gets polarized, gets purely plane polarized. So in this first picture here, the polarization of light is shown by the pink arrows as well as by the pink dots. The pink dots simply represent a polarization vector that is perpendicular to the plane of the paper, right? So here we have two kinds of polarizations, and actually since this is unpolarized light, the polarization vector is everywhere, right? So everywhere on the plane that is perpendicular to the plane of incidence, right? So once that light gets reflected, this initial angle is adjusted in such a way that the relative angle between the refracted ray and the reflected ray is exactly equal to 90 degrees. And when that happens, the ray of light that comes out as reflected only has the polarization that is perpendicular to the plane of the incidence. Okay, so a consequence of this is that if the original ray of light was polarized by itself, and it had only the polarization that is along the plane of incidence, right? This polarization is on the plane of incidence. Then, since there was no component of light that is polarized perpendicular to the plane of the paper, then the reflected ray will have no such component, right? Because of that, there will be absolutely no reflected ray. And the refracted ray would also be polarized. Okay, so if I take an incident ray of light that is polarized, right, and that polarization is parallel to the plane of incidence, then the refracted ray is also polarized and there is no reflected ray. And this happens when the angle between the reflected ray and the refracted ray is exactly equal to 90 degrees. All right, so we want to figure out this angle of incidence because it is so important, because if we have a ray of light that is unpolarized and then we want to make it polarized, this is a method that we can use to make it polarized by using the refraction technique, the refraction reflection technique, and then the reflected ray would be particularly polarized in a certain direction. Okay, so how do we do that? Well, so let's just apply Snell's law to this first picture over here. So if I apply Snell's law, then N air times sine theta p in that picture looks like that is equal to N glass times sine theta 2. Okay, so now I'm doing this for air and glass, but we could as well do this for medium 1 and medium 2, right? So in the case that if I have medium 1 and medium 2, it's just going to be N1 sine theta p is equal to N2 sine theta 2. Okay, but now let's look at the angle over here. That's 180 degrees because that's a straight line. The dashed line is a straight line, the normal, right? So looking at that picture, we can first also realize the fact that this angle over here, that part, is just the reflected angle. And law of reflection says that the angle of reflection is equal to the angle of incidence, which means that this angle is also theta p. Okay, so if that angle is theta p, this angle over here is 90 degrees, and that angle over there is theta 2, then we can also write that theta p plus 90 degrees plus theta 2, that sum total of those three angles must be equal to 180 degrees. Or in other words, if I just rearrange stuff, then I get theta 2 is equal to 180 degrees minus 90 degrees minus theta p. Or this is equal to 90 degrees minus theta p. Okay, so let's take this and plug this back into our equation over here in the Snell's law relationship. Then we have N1 sine theta p is equal to N2 sine 90 degrees minus theta p. But what is sine 90 degrees minus theta p? That's also equal to cosine of theta p. So N1 sine theta p is equal to N2 cosine theta p. And we can go one step further, divide both sides by cosine of theta and divide both sides by N1. So we have N1 sine theta p divided by N1 cosine theta p. So if I do that division, then on the other side also I have to divide by the same stuff, N2 cosine theta p divided by N1 cosine theta p. So here the N1s will cancel, there the cosine theta p's will cancel, and so we will have tangent of theta p is equal to N2 over N1, because tangent of theta p, because sine theta p over cosine theta p, that's tangent of theta p. All right, so that tells us that theta p is equal to arctangent or tangent inverse of N2 over N1. And this is referred to as the Brewster angle. So in order to use polarization by reflection, we have to have a ray of light or beam of light be incident at the Brewster angle. The angle of incidence has to be Brewster angle. And in that case, the polarized reflected ray and the unpolarized or slightly polarized refracted ray, right? Those will be at an angle 90 degrees. Okay, so that's essentially everything about polarization. I hope you enjoyed this video. If you have feedback, please email me at bhattach@ltu.edu. Thanks a lot.